Hello, Aragoneses here. Let's start this course by reviewing the Newtonian physics we already know. A long time ago, when you were in kindergarten or at some point in elementary school, you were introduced to Newton's laws. An object at rest with uniform motion, in the absence of external forces, remains at rest or with uniform motion. When acted upon by an external force, the object experiences an acceleration proportional to the inverse of its mass. Forces come in pairs, each one acting on each of the two interacting objects. Those two forces are equal in magnitude and opposite in direction. We write Newton's second law as m times the second derivative of the position with respect to time equals to the net force. Or in Newtonian notation, m times r two dots, where each dot refers to a time derivative of r. This is a differential equation, well, three differential equations, that once we know all the forces acting on the object, we need to solve to know the motion of the object. It happens for a point particle. If the physical system is not a point particle, then things can be a bit more messy, but we can do it, or at least our computers can do it. You decompose your physical system into lots of point particles, then you need to write Newton's second law for all the point particles and solve simultaneously all three n differential equations. That's the power of Newton's equation, the only one you need to solve. Let's think of a simple example, the pendulum. Assume you have a bob hanging through a string to the ceiling and you make it oscillate. You know its mass because you measure it, and you know the length of the string because you also measure it. How do you describe the motion of this bob? What is going to be the position of the three dimensions of space as functions of time? Well, the first thing you should notice is that its motion is going to be it's not going to be an arbitrary motion. In this example, we can clearly see some constraints to the motion. The bob is going to oscillate on a plane, so your problem is really only a two-dimensional problem. But also you know that the distance from the bob to the point in the ceiling where the string is attached, this distance is going to be constant and equal to the length of the string. Now this seems a good thing. So it's only one-dimensional problem, so some simplifications are here. We don't care about the unnecessary, not relevant coordinates. We can focus only on the angle made between the string and the vertical. That's the only relevant coordinate here, just one-dimensional problem. So constraints simplify the problem and allow us to only track the relevant coordinates. But we need to think broadly when we talk about coordinates. Cartesian's x, y, and z coordinates will not always be the good choice. For example, think about the motion of a planet revolving a star. This star system is moving through space with respect to us. This would be the trajectory of the planet if we were lucky enough to have our visual perpendicular to the plane of the motion. But this is kind of tricky, isn't it? Now, if we choose as our coordinates that of the center of mass of the system and the relative position, then we'll recover a straight line for the motion of the center of mass through space and an ellipse for the motion of the planet around the star, which makes more sense and it's easier to play with. So the choice of coordinates is important, and the choice of position variables we want to work with too. Even though those positions do not correspond to any physical object, as in the case of the stars and the planet, that it was the center of mass and the relative position. So we're going to be working with this kind of analysis that is going to be very, very helpful in order to solve the problems and describe the motion of our physical systems.